Welcome to the deep dive. We've got a really fascinating mission today.
I definitely do. It's a fun one.
Yeah. We are looking at a slide deck titled LGD Theory.pptx, and it covers the Landau-Ginzburg-Devonshire theory for pneumatic ferroelectric liquid crystals.
Which is quite a mouthful.
I know that string of words sounds like a final exam question designed to induce panic, but we have tailored today's discussion specifically for you.
Exactly.
We're imagining you as an undergraduate physics student. You know your way around classical mechanics, you understand electromagnetism, but maybe you're totally new to the specific world of ferroelectrics.
Which is a really common place to be.
Right. So we're going to translate this dense theoretical framework into the physical intuition you actually need. Okay, let's unpack this. Where do we even begin with LGD theory?
Well, we start by looking at the forest rather than the trees. LGD theory is what physicists call a phenomenological theory.
Meaning we're not doing quantum mechanics here.
Right, no. We aren't going to get bogged down in calculating the quantum mechanical interactions of every single atom in a lattice. That would be impossible. Instead, LGD theory uses a macro-level mathematical framework.
It's sort of zooming out.
Yeah, zooming out. It relies on a mean field approximation to describe how these materials behave across different physical states.
So it doesn't matter if it's a huge crystal or a tiny film.
Exactly. Whether that material is sitting as a large bulk crystal on a lab bench, or deposited as a microscopic thin film, or even squeezed into nanoscale pores, this theory gives us a continuous mathematical function.
It maps it all out.
It creates this sweeping landscape of energy that allows us to predict exactly how the material will act under varying conditions.
And what makes the research we're diving into so compelling is that these equations do more than just explain everyday material behavior.
Oh, they do a lot more.
They actually point to hidden, unstable physics. There's a concept tucked inside this math called negative capacitance.
Which sounds impossible.
Right, but it's an anomaly that researchers believe could shatter the current limitations of modern electronics. It could help us build the ultra-low-power computer chips of the future.
It's the holy grail of low-power computing.
But before we get to the groundbreaking applications, the word ferroelectric itself can sound a bit intimidating. How can we ground this concept in something our undergrad listener already knows from, say, their intro physics courses?
Think back to your lessons on magnetism, specifically the Ising model of ferromagnetism.
Oh yeah, the grid of spins.
Exactly. In the Ising model, you have a grid of magnetic spins. If the interaction energy between neighboring spins, usually denoted by J, is greater than 0, those neighbors want to align with each other.
It's easier.
Because it achieves a lower energy state. Yeah. If one points up, its neighbor wants to point up. They do this because aligning with the same sign achieves a much more stable thermodynamic state.
And if they point in opposite directions?
Then they're fighting each other, and it costs the system energy.
So the system inherently wants to be uniform so it can settle into the lowest possible energy state.
Exactly. And ferroelectricity relies on that exact same principle of symmetry breaking. It's just applied to electric dipoles instead of magnetic spins.
So instead of a north and south pole, we have positive and negative charges.
Right. Imagine a material filled with tiny electric dipoles, little molecules or unit cells that are slightly positive on one end and slightly negative on the other.
And they interact just like the magnets.
They do. Because of their spatial interactions, these dipoles strongly prefer to align with one another. When they do align, they form microscopic neighborhoods called domains.
And inside those domains.
Inside a given domain, all the dipoles point the exact same way. This creates a macroscopic spontaneous polarization, which we denote with the variable P.
P for polarization.
Right. And because the underlying crystal structure is usually symmetric, there are two perfectly equal and stable energy states. All dipoles pointing up, which we call positive P, or all dipoles pointing down, which is negative P.
And to jump in here and point out why this spontaneous alignment matters to you and the technology you use every single day, it is the entire reason these materials are used for non-volatile memory.
It's a perfect binary system.
Exactly.
Yeah.
Because there are two distinct stable states, up or down, plus or minus. You have a physical microscopic representation of a binary 1 and a 0.
And it stays that way.
Yeah, because those states are thermodynamically stable. The material remembers that state even when you pull the plug and turn the power off. It's an incredibly elegant way to store data.
But to actually engineer those memory chips, we need to mathematically model exactly how and when that polarization flips from a 1 to a 0.
Which is where the math comes in.
Right. That brings us to the core framework of today's deep dive. The LGD free energy functional. In thermodynamics, physical systems always seek to minimize their free energy.
They want to roll to the bottom of the hill.
Exactly. The LGD theory models this free energy landscape by combining four distinct mathematical pillars into one master equation.
Okay, let's break those four pillars down for everyone. Looking at the first one, the Landau term. There's a lot of algebra here involving an expansion of even powers of the polarization.
Alpha p squared, beta p to the fourth, gamma p to the sixth.
Yeah, all of that. What is this actually trying to tell us about the material?
You can think of the Landau term as the core DNA of the material's energy landscape. You don't need to memorize the algebra, but you should understand the master variable driving it, which is typically called alpha.
The alpha parameter.
Right. Alpha acts like a temperature dial. The sign of alpha dictates the fundamental state of the material. If alpha is a positive number, the material is in a ferroelectric phase.
Meaning no memory.
Meaning it has no spontaneous polarization on its own, the dipoles are totally disordered, but as the temperature drops below a critical threshold, alpha becomes negative.
And that changes everything.
That is the exact moment the material undergoes a phase transition and becomes ferroelectric. It suddenly wakes up and wants to hold a permanent polarization.
And what about the higher order math in that pillar? The terms expanding to the fourth and sixth powers of polarization.
The beta and gamma terms, they basically act as thermodynamic guardrails.
Guardrails.
Yeah, because when alpha goes negative, that initial p squared term would just push the energy down to negative infinity, which obviously isn't physically possible in the real world.
Right, the universe doesn't allow infinite energy drops.
No. So the higher order terms use positive constants to eventually pull the energy back up at high levels of polarization. They control the exact shape of the energy landscape and keep the mathematical model grounded in physical reality.
So it settles at a specific, finite value.
Exactly.
Moving to the second pillar, the Ginzburg term. This one brings in a spatial gradient, tracking how polarization changes across distance.
The gradient of p squared.
Yeah. And a helpful visual analogy for this, I think, is to picture the Ginzburg term as a thick rubber band that heavily penalizes any sharp, sudden changes in the polarization's direction.
That's a great way to think of it. The Ginzburg term is measuring the energy cost of non-uniformity.
Because it doesn't want to change abruptly.
Right. If you have a domain pointing up right next to a domain pointing down, the boundary between them is called a domain wall. The polarization has to physically flip its orientation across that microscopic wall.
It has to transition.
And the Ginzburg term determines how wide and how stiff those domain walls are. If you're analyzing a massive bulk crystal, you might be able to ignore this gradient penalty.
Because the walls are tiny compared to the bulk.
Exactly. But when you are studying nanoscale thin films or complex vortex structures where the polarization is constantly twisting and turning, this spatial penalty is absolutely critical to the math.
Which brings us to the third pillar, the Devonshire term. This involves elastic stiffness and strain.
Now we're getting mechanical.
Yeah, we are moving from purely electrical behavior into mechanical deformation.
The Devonshire term handles the mechanical toll booth of the system, so to speak. It couples the electrical polarization to the physical squeezing or stretching of the material.
Through electrostrictive coefficients.
Right. When those millions of dipoles align to create polarization, the physical crystal lattice of the material actually distorts slightly. It elongates or contracts.
It changes shape.
In large, unconstrained bulk materials, the system is completely free to relax and change shape. So physicists often just absorb this mechanical energy mathematically into the Landau parameters to simplify things.
Make the math easier. But the research emphasizes that we can't always take that shortcut, especially with modern electronics.
Definitely not. In thin films, you are usually growing the ferroelectric material layer by layer on top of a rigid crystalline substrate.
Like silicon or something.
Right. And that substrate has its own atomic spacing. It physically forces the thin ferroelectric film to stretch or compress to match it. This locks a permanent physical strain into the material.
And because of that Devonshire coupling.
Exactly. Because of that coupling, this mechanical squeezing actually shifts the electrical phase transition temperature.
That's wild.
Yeah.
You are literally altering the electrical memory properties of the chip by mechanically stretching its atomic lattice.
It is wild. That interconnectedness is what makes condensed matter physics so fascinating to study.
All right, the final pillar, the fourth one. the electrostatic term. This one seems to account for the push and pull of electric fields.
It accounts for two major electrical interactions. The first is the interaction with an external electric field.
Like applying a voltage.
Exactly. If you apply a voltage across the material, this term dictates how that external field tries to force the internal polarization to align with it.
And the second part.
The second part deals with internal depolarization energy. If the polarization abruptly ends, say, at the visible surface of a thin film, it creates an enormous internal electric field that actually fights against the material's own polarization.
We'll definitely come back to that because that's a huge issue. But if we connect this to the bigger picture, why do we need all four of these massive mathematical pillars working simultaneously?
If we connect this to the bigger picture, combining these four pillars gives physicists ultimate predictive power. Once you define this total free energy equation, you aren't just guessing anymore.
You have a map.
You have a perfect map. You can predict almost everything about a novel material before you even synthesize it in the lab. The shape of the domain walls, the complex phase diagrams, how it responds to mechanical stress.
And the voltage.
Yes, most importantly, the exact voltage you need to apply to flip the memory state from a 1 to a 0.
Let's actually visualize that predictive math right now, because graphing these equations reveals the core behavior of the material.
Visuals always help.
So imagine a classic Cartesian graph. The x-axis is the total free energy, and the x-axis is the material's polarization. Let's look at the high-temperature ferroelectric phase first, where that alpha parameter is positive.
In that phase, the graph is just a simple, single U-shaped valley, a basic parabola. The lowest point, the minimum energy, is right at the center where polarization is 0.
So it just rests there.
If you leave the material alone, it rests perfectly at 0. If you apply an electric field to it, its response is just a straightforward linear line. It polarizes slightly while the field is on and drops right back to 0 when you turn it off.
No memory.
No hysteresis and therefore no memory.
But when we drop the temperature and enter the ferroelectric phase, where alpha goes negative, this is where the famous double well appears.
The W shape.
Yeah, the single valley bulges up in the center, and the whole graph looks exactly like the letter W.
Because alpha is negative, the 0 point at the center of the graph is no longer a comfortable valley. It becomes an unstable peak.
Like balancing a ball on a hill.
Exactly. A theoretical ball placed right at 0 polarization would immediately roll down the hill into one of the two new valleys on either side.
The positive and negative states.
Those deep valleys represent positive P and negative P. The spontaneous polarization states we discussed earlier, the material is fundamentally forced to choose a side, breaking the symmetry of the system.
Here's where it gets really interesting. If you take the mathematical derivative of that W-shaped energy landscape, you get a completely new graph.
The hysteresis loop.
Yes. This time, polarization is on the y-axis, and the applied electric field is on the x-axis. The resulting curve from that derivative is this incredibly elegant S-shape. It starts flat, curves up sharply, and then flattens out again at the top.
That S-shaped curve is the theoretical hallmark of LGD theory. It perfectly captures the hysteresis loop. It shows how the material stubbornly resists changing its polarization state until the external electric field gets strong enough to violently push it over that unstable energy peak in the middle of the W.
And once it crosses that peak,
The moment it crosses that peak, it snaps instantly into the opposite state.
the research also highlights a sort of messy cousin to these materials called relaxer ferroelectrics. How does their energy landscape differ from that perfect W shape?
Relaxers are fascinating. They have nanoscale chemical disorder intentionally built into their crystal structure.
So they aren't perfectly uniform.
Right. This microscopic disorder disrupts the long-range alignment of the dipoles. So instead of a deep, highly defined W shape, their energy landscape is flattened out and diffuse.
A shallow W.
A very shallow double well. Consequently, when you plot their response to an electric field, the S-curve isn't a sharp, snappy loop. It's slanted, less abrupt, and much more smeared out.
So the transition is smoother.
We call it a diffuse phase transition, which is highly useful for specific types of sensors and actuators, even if it's less ideal for binary memory.
So this perfect S-curve sounds phenomenal on paper for memory.
Mm-hmm.
We have our reliable state sitting in deep energy wells. But reality is a bit messier, especially when we try to shrink these materials down into the microscopic thin films we actually use in computers.
It gets very messy.
The moment we make them thin, they start trying to destroy themselves. Let's talk about the threat of depolarization. You brought it up briefly earlier.
This is perhaps the most crucial practical problem in ferroelectric engineering. Let's say you take our perfectly polarized material and slice it into an ultra-thin film.
Just a few nanometers thick.
Right. Because it has spontaneous polarization, all the tiny positive dipole heads are pointing up toward the top surface, and all the negative tails are pointing down toward the bottom surface.
And what actually happens when those aligned dipoles hit the physical boundary of the material, space just ends.
They create what physicists call bound charges right at the bare surfaces. You end up with a dense sheet of positive charge sitting on the top surface and a sheet of negative charge on the bottom.
Which creates a field.
Exactly. According to the foundational laws of electromagnetism, separating positive and negative charges across a distance creates an electric field between them. This is the internal depolarization field.
And because it's a thin film?
The physical distance between the top and bottom is microscopic. That tight spacing makes this internal field incredibly strong. It can reach hundreds of megavolts per meter.
That is massive.
It is, and it points in the exact opposite direction of the material's own internal polarization.
So if left entirely alone, this massive depolarization field would literally tear the material's domain structure apart.
It would.
The internal field is so overwhelmingly strong, it would force the dipoles to flip and the net polarization to collapse completely back to zero.
The material is essentially a victim to its own geometry.
If this field wasn't neutralized somehow, building thin film ferroelectric memory for our phones and computers would be completely impossible. So what saves it?
The solution is sandwiching that ferroelectric thin film between two metal electrodes.
Metal to the rescue.
Always. Metals are defined by having a vast sea of highly mobile free electrons. The instant those bound charges try to accumulate on the surface of the ferroelectric layer, the metal electrodes react.
We're talking about an incredibly fast reaction time, right?
The timescale is on the order of femtoseconds to picoseconds, a millionth of a billionth of a second.
Practically instant.
The top electrode instantly injects mobile negative charges to perfectly cancel out the positive bound charges. Simultaneously, the bottom electrode injects positive charges to cancel the negative bound charges.
Screening.
Yes. This near-instantaneous process is called screening. It completely neutralizes that massive depolarization field, allowing the delicate ferroelectric structure inside the thin film to remain polarized, stable, and useful.
It's like the metal electrodes are jumping on a thermodynamic grenade the moment the pin is pulled.
That's a great analogy.
And this lightning-fast screening process actually hides one of the most bizarre phenomena predicted by the LGD equations. Let's look back at that theoretical S-shaped curve of polarization versus electric field. If you trace the middle of that S, the line actually bends backward.
It does, and the slope of a polarization versus electric field curve gives you the electrical capacitance of the material.
So if it bends backward,
In that middle region where the S bends backward, the slope is negative. This means the capacitance itself is negative. The ratio of the change in polarization to the change in electric field literally drops below zero.
but in normal physics, a system sitting in a negative capacitance state is thermodynamically unstable.
Completely unstable.
Imagine you're trying to balance a sharp pencil perfectly on its tip. A tiny breeze, a tiny fluctuation, and it falls over. It shouldn't exist in a steady state
And in standard everyday measurements, it doesn't,
because of the metals.
because those metal electrodes screen changes in femtoseconds. The moment the material tries to enter that unstable backward bending region during a switching event, the free charges rush in.
And it just bypasses it.
The polarization snaps instantly to the other stable valley. It physically skips right over the unstable negative capacitance region. It is entirely predicted by the LGD math, but it is heavily obscured in practical reality by the sheer speed of the surrounding electrodes.
The math proves it's there, but the universe covers it up before our instruments can easily capture it. Now, to wrap up our journey through this framework, the research pivots to a highly specific, cutting-edge application that takes everything we've learned down to the extreme nanoscale.
The liquid crystals.
Yeah. The research zeroes in on one specific pneumatic ferroelectric liquid crystal, a material known as RM734. But instead of studying it in a bulk pool, they trap it inside tiny one-dimensional tubes called AAO nanoporous structures.
We are talking about confining this complex liquid crystal into microscopic rigid cylinders.
Getting a liquid crystal perfectly aligned inside a nanoscale tube is a massive practical challenge in a laboratory. But from a theoretical physics perspective, how does this extreme geometric trick actually simplify the math for us?
Well, because the physical confinement is so extreme, the long, rod-like molecules of the liquid crystal are forcefully aligned along the long axis of the pore.
They don't have room to wiggle sideways.
Exactly. The polarization is completely locked into a single dimension. Furthermore, the physical distance between the individual pores in the AAO template is large enough that the electrostatic interaction between different pores drops to zero.
So they don't talk to each other.
Right. Each microscopic tube acts like an isolated single nano-island.
So instead of dealing with complex, three-dimensional vectors twisting in all directions and interacting with each other, physicists get to treat this system as a quasi-1D uniaxial ferroelectric.
The dense multivariable calculus just collapses.
It collapses down to a single scalar polarization parameter along the z-axis. It is a beautiful mathematical trick born from a complex physical setup.
It is a profound simplification that allows for incredibly precise modeling. But the researchers don't just want to know the static final resting state of the liquid crystal. They want to know how it reacts and moves in real time.
How it flips.
Yeah. To do this, they introduce an essential upgrade to the LGD equations we've been discussing, the time-dependent Ginzburg-Landau equation, or TDGL.
The LGD equations we discussed so far are essentially static maps. They map out the energy landscape, showing us where the thermodynamic hills and valleys are. TDGL is the math that actually lets you press play and watch the system move across that map.
Exactly. The TDGL equation takes the mathematical derivative of the free energy functional with respect to the polarization. But instead of setting it to zero to find the resting state, it sets it equal to the change in polarization over time.
So time becomes a variable.
It adds a time derivative multiplied by a crucial parameter called the relaxation coefficient. This coefficient represents the internal friction of the system. It determines exactly how fast or slow the material physically responds to thermodynamic forces.
So by applying TDGL to this 1D nanopore system, you can literally simulate the exact millisecond by millisecond movie of how the polarization evolves.
You watch the whole process unfold.
You can watch how the domains nucleate and grow, and how the entire liquid crystal reacts the moment you apply an external voltage across the tube. It takes the static W-shaped energy landscape and dynamically animates it.
It perfectly bridges the gap between theoretical thermodynamics and actual dynamic device engineering. With TDGL, you can see the spatial effects of the domain wall stiffness from the Ginzburg term, the deep phase stability from the Landau term, and the driving force of the external fields from the electrostatic term, all playing out and interacting over time.
So what does this all mean? Let's quickly recap our journey. We started by grounding ferroelectricity in the simple concept of dipoles wanting to align to save energy.
Just like the Ising model.
Exactly. We built the master equation, the LGD free energy functional, out of 4 pillars: phase transitions, spatial gradients, mechanical strain, and electric fields. We visualized how those exact equations create the double-wall energy landscapes and the fundamental S-shaped curves.
And we saw the depolarization threat.
We explored how the incredible speed of metal electrodes provides screening, saving thin films from destroying themselves with their own internal depolarization fields. And finally, we saw how confining materials into nanopores and applying time-dependent math lets us animate these processes. LGD theory isn't just abstract algebra. It is the fundamental toolkit for engineering the next generation of materials.
This raises an important question, though, one that pushes right against the absolute edge of modern physics. We established that the theoretical negative capacitance region in the middle of the S-curve is naturally hidden.
Because it's unstable.
It is thermodynamically unstable, and those lightning-fast metal electrodes screen it out before we can ever utilize it. But what if we didn't use perfect metals?
Oh, interesting.
What if we could engineer a specific material interface or a clever dielectric circuit that intentionally slows down that screening process just enough to catch the ferroelectric in the act?
Trap it on the peak.
If we can stabilize and trap the material right in that negative capacitance state, it acts as an internal voltage amplifier. The research suggests this could shatter the current power limits of silicon transistors, enabling highly efficient, ultra-low power devices.
The stakes there are massive. We are hitting a thermal and power limit in how small and fast we can make computer chips, often called the power wall.
It's a huge bottleneck.
Imagine exploiting the very thermodynamic instability of a ferroelectric material to break past that wall, potentially dropping the power consumption of our phones and data centers by orders of magnitude. I encourage you to ponder that exact question as you continue your physics studies. Don't just look at the stable, comfortable valleys of the equations you study. Look closely at the unstable peaks. That might just be where the next major technological revolution is hiding. Thank you for joining us on this deep dive. Keep questioning, keep learning, and we'll catch you next time.